Yesterday we talked about a theorem that told us how many zeros there are. And today we're going to make a list of all the possible zeros. So what could they be? And then we could theoretically put those two together and then actually find them. If we knew how many there are and what they could possibly be, then we could theoretically find them. So today we're going to make a list of all the possible zeros for a given function, all the real zeros. So anybody remember what the word rational? What should you think when you see rational? Huh? Rational, what does that mean? What's a rational function? Yeah, the fraction function, right? So we think rational, think fraction. So we're going to basically write these zeros all as fractions. So rational zeros theorem. There we go. This one I promise is actually easier. Alright, so rational zeros theorem says this. Not named after anybody in particular, but still equally as important probably. So if we have a polynomial function, only works for polynomials. Each real zero must be of the form plus and minus p over q. This is the form that our zeros have to be. Obviously, we don't know what p and q are yet, but all of our zeros are going to be in this fraction form. Anybody have an idea where p and q come from? Heard this statement, mind your p's and q's. That unfortunately does not come from this, but maybe make up that does. So P is the factors of the constant. So find the constant, and we're going to list all the factors of that constant. That's going to be our P values. And our Q values come from the factors of the leading coefficients. So P are the factors of the constant, and Q are the factors of the leading coefficient. That's where we get our P's and Q's. And then we're going to write them as these ratios, fractions, and that will make a list of all of the possible real zeros. And then what we could theoretically do is then check which ones are actual zeros, and good to go. The rest will be imaginary. Good. All right, let's try one out. So we're going to be making a list of all of the potential or possible real zeros. We've got a polynomial, just like to write it out. And the first thing we're going to do is find what P and what Q are. All right, so what's P? Factors of the constant. Yeah, just one. That's it, actually, in this one. We'll start with an easy one. So this gives us our P's. Right there. And the only factors of one are, well, 1 and 1. Just 1. That's easy. All right, Q are the factors of the leading coefficient. So what are the factors of 3? Only 1 and 3, right? So, no other way to get 3. So now we're just going to write our fractions here, if you will. So our possible real zeros are of the form plus or minus p over q. So what we do is we just write each p over each q and put a plus or minus in front. So plus or minus 1 over 1 and plus or minus 1 over 3. And generally we would simplify this. 1 over 1 you can just write as 1. And you can even do that when you write it the first time if you want to. And 1/3. Those are the only numbers that are possible for the real zeros. There's only 4 possibilities. It wouldn't be that hard to then check these. We could check them using synthetic division. Figure out how many there are. All right, that's it. That's the end of the theorem. Easy, right? Let's try another one. What was that hard, wasn't it? All right, so this one's almost the same. It's a little bit different function. Another easy one. So our P and our Q, just need to identify those. Now the sign doesn't matter. So this P is a -3. It doesn't matter because we have to write in a plus or minus in front of all of them anyhow. So you don't need to worry about what sign it is. You just need to take the number and whatever number right there. So our P this time is going to be 1 and 3. Okay. And the Q is just the invisible 1 there. It's not 0, it's invisible 1. Q is just one possibility is 1. This is just the opposite. Our possible zeros. And we do P over Q. So 1 over 1, which we know that reduces to 1. So it's just write plus or minus 1. And plus or minus 3 over 1 or just 3. There are only 4 possibilities for this one as well, so there's got to be 1, -1, +3, and -3. It's the only possible real zeros of this function. Pretty cool how someone found that out, right? They just looked at patterns of the zeros and determined, well, it always happens to be the factors of this one or this one. Let's try a little harder one. Not too intense yet, but I want that here. -4x² minus x² plus x plus 2. So what are the factors of 2? Yep, 1 and 2. No. Factors of 4? Yeah, 1, 2, and 4. 1 times 4 and 2 times 2. So make sure you get them in the right order. The P is the constants, the Q is the coefficients. All right, now this one's going to be a little bit longer. We're going to do 1 over 1, 1 over 2, 1 over 4. So make sure you keep a pattern. I always just did the first P over all the Q's and then the second P over all the Q's. So possible zeros. Plus or minus 1 over 1. Let's just try to make that 1. Plus or minus 1 over 2. Plus or minus 1 over 4. Plus or minus now 2 over 1. Which now is 2. Plus or minus 2 over 2. Is actually 1. I'll write 2 over 2. See what happens here. And then plus or minus 2 over 4. Then you can obviously reduce some of those in head. Now you also notice that we actually have some duplicates. 2 over 2 is the same thing as 1. So we can wipe that out. And 2 over 4 is the same thing as half. We're going to wipe that out. Really try to condense your list as much as possible so you don't have duplicates there. So there's actually 8 possibilities. So just make sure you kind of purge your list. You don't have multiples there. All right, let's try a little bit harder one. 6 and 9. if it's helpful for you to write out the pairs over the weekend, just think about all the factors of 9. Isn't that many, but if you struggle with coming up those, it's like, well, 1 times 9 is going to be X. Okay? 2 doesn't go into it, 3 does, it's 3 and 3, right? There's no more. So our factors, I always like to write them in order 1, 3, and 9. And then our factors of 6, if you need to do the same, 1 and 6, and 2 and 3, right? No other way to get 6. So 1, 2, 3, 6. We're going to have a little more work to do on this one. We're going to do 1 over 1, 1 over 2, 1 over 3, 1 over 6, 3 over 1, 3 over 2, 3 over 3, 3 over 6. Let's go through this pattern. Alright, so I'm going to go ahead and write them all out. So minus 1 over 1 is 1. Take a minute and do that. So you should at first have 12 total, and then you can reduce them, and then if you can just kind of eliminate them as you go, that's fine too. We're going to keep plus or minus 1, plus or minus half, plus or minus a third, plus or minus a sixth. Always keep all the first group. Plus or minus 3, plus or minus 3 halves. 3 over 3 is 1. 3 sixths is a half. We do need 9. We need 9 halves. We don't need 9 thirds because that's 3. We don't need 9 sixths. That's 3 halves. I got one last one for you guys to try. You can type this one in. We'll do a hard one here. You can just type in your final answers. That's 6 and 20. And you don't have to type in the plus or minus if you don't want to. Here's another idea. If you don't want to type them all in, count how many solutions. You could just write how many solutions there are. That's in Williams' soul. $24. 24 if you don't eliminate them, probably. What do you get? So don't forget, like, 26 is the same thing as 10 thirds. You want to make that. 10 6 is the same thing as 5 thirds. So don't forget to eliminate them. You got 16. Remember decimal 16? That's 16. Alright. Good, there's 16. Alright, hopefully you got the idea. If you do want to go ahead and, you might be actually able to do the whole assignment. It doesn't take long. 34 to 44 evens. And actually,